So welcome everyone. Uh, let's go to today's problem. So today's problems are, we have again 3 problems. This time we have easy, medium and hard. So we'll go through the first problem. So finding a winner on a tic-tac-toe game. You guys can hear me, right? Let me make sure that you can hear me.
Yes.
Great.
Yeah.
So this problem is to find a winner on tic-tac-toe game, and there are 2 players, A and B. A will win if the character is X, either horizontally, diagonally, or clockwise. Same with B, he will win. We put 0 characters, horizontally, diagonally. All right, it's better. So you have been given moves and you have to determine who won. So it's like a very, I would say, like, simulation kind of problem where with every move you have to do something and you have to determine who was the winner. If no one was the winner, then you will say draw. And if the game has not finished, like, if it's a like 3x3 matrix kind of stuff, if you haven't spent, like, all the 9 moves, then you will say pending, as in this particular case. So these are different states you could be in. So any idea, did anyone solve this? So let me try to explain a little bit. I think people who have played this game, they will know immediately, but this is how the game is played. So you have this 3x3 grid. Player A can start from anywhere. Suppose he started with X. Player 2 can say 0. Then player 1 says X. Then player 2 can say anything, like maybe he said X. And player C will say 0, and X, and 0, then X. Right. Did I lose someone's turn? Or if not, then if it was 0's turn, it's like this. So this is the game. You have all these moves given to you and you have to determine who is the winner. So A's turn we put X in that particular coordinate, and in B's turn we put 0. So how can A win? A could have won here if we had, suppose, X here. Then if X was here, then he could win just because of this column. He could have won. He could have also won because of this row. And if not, then if there was a, like, diagonal here, X, 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 then he could have win this way, or even this diagonal will work for him. As long as he gets 3 consecutive X in any direction, it will work. There are these directions. These 4 directions. Same with B. For B, like for him, instead of X, he has to get zeros in these 4 directions. So any idea?
I'll iterate all the moves array, and each time I deal with 2 moves. The first move is for player A, and another move is for player B. And we have 2 array. play A and play B, each array has 9 elements. You
Right.
can number from 0 to 8, and these 9 elements to mark the which position is 1. If that position is 0, that means there is no Tic-Tac-Toe on in that position. If it's turned to 1, that means I have a move to that position. And each time you check which one, play A or play B, is win. That means the aggregate number is 2, 3.
Right.
You can
Right.
return the win. Yeah.
Yeah. I mean, yeah, this straightforward approach. So yeah, right. So we start with A's move, right? So you know that first move is A's move, or let's call it 0th move. Like, you are given a move array, right? So you have been given this moves. So first one we will apply for A. So we can use this index to choose, okay, this is first one. So let's update A's status. And what A cares about for his winning is he will keep a count of his rows, columns, as we said, like, rows for A, let's call it A rows, A calls, and then A is diagonal because we have these two directions here, right? This one and this one. So A diagonal, and then second diagonal, call it anti-diagonal or something. So rows and column you can always update for any coordinate, right? But for diagonal, what is our focus is this diagonal and this diagonal. So how do you determine based on the X and Y coordinate, or like X and Y point, like where we are? Because I don't care about this diagonal, for example. I don't care about this diagonal. I also don't care about this diagonal. I don't care about this diagonal or this diagonal. What is important is this, the biggest one, this one and this one, for the, like, for the winning. So if you put some values, 0, 1, 2 is the row, similarly column, you can determine a relation here for this line and this line, right? Does anybody know what we can say about XY when they are in one of these diagonal?
We can multiply row by 3 and plus column value, and translate the 2D array to 1D array. Like for example, 0, 0, we got A0, and 0, 1, we got 1, and 0, 2, we got 2, and 1, 0, we got 3. Yeah.
So what I am saying, that if I have to determine whether in his move he was able to get any stuff on these like, boxes, if you look at these boxes, you can see, let's call this is X, let's call this is Y. So what is value of X plus Y here? X plus Y here is 2, right? What is the value of X plus Y here? It is 2. Here, what is the value of X plus Y? It is 2, right? For that particular diagonal. So once you get a point and you know which X and Y coordinate I can derive from that point, if this gives you X plus Y equal to 2, you know that you are on this diagonal. Similarly, you have another diagonal to think about, right? So can you similarly see what is like, can we derive that? There is a chat message. I will try to take a look in the meantime.
Is that x minus y equals 0 for the other diagonal?
Right, right. So for the other diagonal, let's call it anti-diagonal, one of these. So yes. So in this case, like if you see x minus y is constant, it's not changing. So now when you get a point for A, like, if it's A's move, he can, because his point is always in any row. So he can keep, updating his rows, his columns. But for diagonal, he has to check whether the point is landing in one of these, columns. Sorry, one of these diagonals. So he will continue updating that if it's valid. And at any point of time, if any of these become 3, then he knows that he has won. Same with the, next one, like, for B, he will have exactly similar kind of calculation. And that's it, I think. It's the implementation problem, not much logic, but yeah, how cleanly you can do it. And I brought up this diagonal thing because this will be useful in other problems. This is a very useful things to realize in metrics. So yeah, and you will also keep count for how many points we have already visited, because if nobody won so far and we have already used all the 9 moves, then it is a draw. But if there are only, say, like 2 moves and there is no winner, in that case you have to say, hey, the game is not finished yet, it is in pending status. So that's the problem.
What is the data structure of, like, for example, a row?
You can use, I think, arrays would work.
Yes, arrays will work. And I also just want to add on what Roger said, that this approach is very useful for a lot of similar problems. One good example is n queens problem.
Mm-hmm. Yeah, true. So that is why, the main thing here, I would say, just make sure that you understand these things in these kind of problems. Uh, plus, plus one more thing which I was thinking was important was, yeah, we excluded these kind of things here, right, in this particular problem because it didn't make sense. But in some other problems, it may make sense to derive that also. So that's it. I mean, we can move ahead, or is there any problem? Any more discussions needed here?
Do you have a solution for this?
Yeah, we have a solution. I mean, you want me to share it? It's I can share.
Yeah, just showing the code on how this approach works. I believe it will be super helpful.
Sure. Let me try to share that. Sorry guys, I'm slow today. For some reason, I don't know even how to share this thing. Oh my God. So. Okay, I don't get options to, it's hidden somewhere for some reason. Let me. Okay, finally. Okay, so the approach we talked about, you can see my screen now, right? this is what we just talked about. You have these, like, A has A rows, A calls, B rows, B calls, and these diagonals, as we talked up to this. And then we check for each move what is the row and column we got here. And then we'll check whose turn is this. If it was A's turn, then we just increase his row and column numbers. Then we check, this is R minus C equal to 0 equation. So we add one of the diagonals count. With R plus C equal to 2, we update another diagonal. And if any of these became A, then we are returning A. Same thing we will do if this was not A's turn. We will do the same thing for B. And then we keep count of move. If move's length was 9 and nobody has won yet, that means it's draw, or else it's pending. Does that make sense?
Yes.
Okay.
If anyone has any questions, please ask.
So is there like we can solve like taking A, like X moves as 1 and O moves as -1, and we need to check the count. If there is a -3, then the answer is B, and if it is a +3, the answer is A.
Right, but in that count, you have to make sure, if you determine that, just make sure that the direction also matters. Like, so if it is row wise and you are updating your count, then it's fine. But if it was in a different row, let me share on my screen then make sure that you don't update in that particular case. So something like here, suppose it was A's move. So first move A did here, right? And then next move A did here. Like B did some move, suppose, for example, okay, actually, let's make it X. This was A's turn. B's move is 0. So what will you do for A's count in this particular case? Because A's move here versus here means different thing in terms of row, right?
So what I was thinking, we need to take that same thing, rows and columns and diagonals. We need to make, if there is a 3 in, for example, in A, if there is a 3 in a diagonal, if we need to increase the count instead of just taking the places, like array of that size, we need to increase that variable like count.
Okay, so I'm not following. I'm pretty sure what you are saying makes sense, but the thing is, I don't understand because I haven't thought in that way.
Hey, like Roger, I believe like what Sonia is trying to say right now, like we have two different arrays, like for A columns and B columns. Okay, so what she's suggesting, let's say we use, instead of like two different arrays, one for A column, one for B column. I'm just taking like a column example.
Yeah.
Okay, instead use like a single array for column, and
Okay.
if it is the A move, be incremented by +1. If it is a B move, be decrement by -1.
Oh,
Okay.
I see.
So at the end, like if result is 3 or -3, then
right,
it indicates A won or like B won.
got it.
That is doable.
Yes, that makes sense. Now I understand what she's saying. And the same for diagonal also, right? That row you can do, column you can do. What do you do with diagonal? Like, you update just one array? I'm just curious, like it is just one array for A? Actually, there is total one array. Okay.
It will be same for diagonal.
Okay, got it. Yeah, because if it is 3, then you know that it was A who won. Otherwise, if it is -3, then B who won, right? Yeah, it's a good approach. Feel free to share this code afterwards. Should work. Should we move to the next one? Because this particular problem is very implementation oriented. It's like not much logic, but how you keep count of every directions, and as cleanly as you can do that, it will be easier to write code for it. All right, then let's go to the next problem then. So today let's do hard problem first. But it's kind of similar what we were just talking, and I think it's not very hard. So this is grid illumination problem. In this, you are given n cross n grid. For example, this is the one grid. I will explain later also. And so there are lamps on this grid at different point. So here 0, 0 means if your matrix was, for example, 5 by 5, then here there is a lamp at this location, 1. There is another lamp at 4 by 4. So another lamp is here. So these lamps will illuminate horizontally, vertically, and diagonally. So that is why everything in this last column is illuminated because of this guy. Towards its left, towards top of it, and leftwards also. It could have illuminated right side also, but there is no area to illuminate, so it's not giving you that one. Same here, this guy is on topmost corner. It can illuminate everything towards it, right, bottom, and diagonally. So this is the current state of the system. Now the question is, if you are given a query 1 1, that means 1 1 means this particular location, then if there was a lamp there, you should have turned it off, and also all its other 8 neighbors, possible 8 neighbors, including itself, total 9 guys. So you have to just make those things 0. Not 0, let's call it uh, unilluminate because of that. So in this particular case, I would like to show you that, hey, like, why this is still on when I was supposed to, turn light off. So the reason is, when we came here, uh, there was a light here. So this guy will got turned off. But the problem is there is another light here. That light can continue illuminating diagonally. So this is still illuminated. So I will draw it to make sure things are clear, but yeah, bear with me for now. And if you were able to find any lamp there, you will return 1, I think. And then if not, which happened in 1 0 case, then you will return 0. That's the output. So that's how the problem is, and we have to solve it for Q. What is the Q? So lamp length is 20,000. Query's length is like 20,000. Okay. Grid is 10 to the power n cross 10 to the power n. Okay. So O of n should be okay. Let's clear it. Okay, so our grid was like this. I forgot the number. I had drawn somewhere, but it's like 5 by 5. So this grid was illuminated. I remember that. So this must be 1, 1, 1, 1, 1, just because it can illuminate everything towards all the directions. So this was the case. And also, so this was like, there was a light here. Let's make a start here. There was another light here. So there is another star here. Because of guy on the bottom, this lamp, it will illuminate also this cell. So this was the state of the system. The rest others are zero, means they are not illuminated. Okay. So first query was on 1, 1. So we said, okay, run query on this guy. So when it will run the query, if there was a light here, it would have switched it off, but there was no light here. So when we are running a query on 1 and 1, our grid will start looking differently. Okay. So it will try to, okay, before I do that, I have to also remember there is another light here. So no matter what happened there, this light will continue illuminating these cells for sure, right? But we had an operation here which will affect these guys. These 9 guys can be affected because of this. Okay. So what can happen is, okay, there is a 1 here. So now nobody can illuminate here because there is no light. Here 1 is illuminated, but there is no light here. So you have to remember also that where the light is, not just illuminated. So there's no light here. Same thing, no one to illuminate this, no one to illuminate this. So everything else will be 0. Similarly, you can, there was another query like 1, 0 or something. So 1, 0 means this one. So it will, there is no light there. And again, it won't affect anything, I think, if it was 1, 0, because its neighbor are basically, this is the neighbor this guy can affect. The only ones which is neighbor to him, which it could affect, is being illuminated by a different light. So nothing will change for him. So, yeah, but as a return, you have to also tell how many lights you were able to turn off. So in this particular case, this guy was able to turn off a light here for sure. So your return will have 1 for the first query. In this particular second case, there was no light which we could turn off. So we will return 0 and that's it. That's why the output is 1, 0. Now, how would we solve it? Has anyone seen this problem earlier or tried to solve it? Think about it for a minute and then we will continue. So in last problem, we did something with matrix that will come handy just to give you some idea. So one thing which is very important is like for each operation, suppose you have been given this matrix to begin with, you know how to traverse the closest members. Maximum you will have total 9 places to traverse. You will look into it, what is the value, but you cannot turn it off. The reason being you cannot turn it off directly because other light could be illuminating it. That is one thing, that it's not feasible to just turn it off. So you have to think like, okay, how can I say that some cell is illuminated or not? Right? So suppose if there is a light here, I have put a light anywhere, this guy can illuminate everything here, everything here, everything here, 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 right? So in these 8 ways, one light can illuminate things. So suppose if there was something in the middle, like suppose here, this guy will illuminate, see, this one, this one, this one, this one, everything. Doesn't matter whether we have light here, 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 you can just continue deleting these lights, but just that guy can continue to illuminate every place. So where a light is very important. Plus any row can be illuminated if we put any light in that particular row. Like for this row to illuminate, if there is any light in any of these cells, it will continue to illuminate, right? Same with any column. For this column to illuminate, if you put any light in this particular column, this is all illuminated as long as light is on. Similarly, for the diagonal also, for one diagonal, for example, just to make this time things interesting, for this diagonal to illuminate, if I have a light here, for example, it can illuminate this one. Even if there is a light here, like here, for example, we can have this entire diagonal illuminated. So that happened with this diagonal. Similarly with the anti-diagonal thing, same story. If we have this anti-diagonal, anywhere we have a light in this particular path, this entire path will be illuminated. So what matters is like where a light is. So for each row, you have a given row, like you have only, for example, suppose 0 to m rows, 0 to n columns, right? 0 to n columns. For any given point, you can figure out, okay, how many diagonals you can have. You can have this diagonal, you can have this diagonal, this diagonal, this diagonal, or you can have diagonal in this way. And the equation we derived last time, there you had x plus y equal to 2, right? And x minus y equal to 0. I mean, how to check I am on any particular diagonal. So any diagonal, if you look at it, like for this thing, this diagonal, this diagonal, this diagonal, x plus y will be constant, not 2, but for this entire thing, your x plus y is constant. Same with this, same with this. For anti-diagonal, same story holds. If you do this, then x minus y will be constant too. So given a point, given like position, can you, if you know the xy coordinate, figuring out row is trivial. You know which row it is. You also know which column it is. You can derive with this equation which diagonal it is, like both diagonals. And then you can have this information that this particular row or this particular diagonal has these many lamps, right? So suppose this is row 1, let's call it row 1, has
Okay.
5 lamps.
Sorry, like a quick question.
Yeah.
So right now, our first goal is to try figuring out how many lamps are in each row or column or like diagonals or
Right,
anti-diagonals.
right,
Okay.
exactly.
So we have to compute that information first, given the number of lamps, like the lamps are in which row or column, and
Mhm.
then we can proceed. Correct?
Totally.
Okay.
Because we saw that even if there was a light in this particular case here, even if I remove this, the other light is still affecting the path. Like it can still illuminate, especially with this particular example. We saw no matter what we do, if there is a light in the center, everything will be illuminated.
Because I haven't solved this problem, but that seems like a first logical step
Yes.
okay, makes sense.
Yeah. Thanks for adding to that. So now, given this, in the beginning itself, you can store this information as Gaurav was saying, that row wise, column wise, diagonal wise, and anti-diagonal wise, how many lights we have to start with. And so you are kind of counting it. So you can use something like map for all these things, all these information. Plus also, since the query asks that you will switch off the light, you have to also keep an status whether a light is on or off at a particular position. I mean, that is additional information you can have. And then you just go through this cell where you are starting. You do your traversal to the neighbors. If there is a light which was there to begin with and which was on, you switch it off, and then you have to return a response 1. If you remember, that is asked in the question, that if you turn off any light, you have to tell how many light you were able to turn off. So 1 or 2, whatever the count you can have, continue updating that, and you will return in the end. And also, uh, that light may be in any row, any column, on any diagonal. So you will have to delete that count. So that's the basic idea. I can show the code again to explain what we just talked about. But before that, if there is a conceptual question, please go ahead now.
I have a question on this x plus y equal to k and x minus y equal to k.
Mm-hmm.
Because with 9 cross 9, we know it was k was 2.
Mm-hmm.
Okay. K was 2 in that case. Now, in this scenario, let's say we have n cross n grid,
Mm-hmm.
how we can figure out that equation.
Yeah. So for example, let's make something like this.
And also, I have other question that in the last tic-tac-toe,
Mm-hmm.
okay, we took 3 rows, 3 columns, okay, 1 diagonal and 1 anti-diagonal,
Mm-hmm.
because that's the information we were interested in.
Right.
Okay, now here we have n rows and columns, okay, which is very trivial to visualize, but how many diagonals and anti-diagonals should be there?
Yeah, we can derive that.
Okay.
So first question is in this particular case, what is different, that we have many diagonals. Like this is one diagonal, this is this diagonal, this is this diagonal. We can call it a diagonal or not, but this is a diagonal, right? So all these diagonals of this shape, right? We have this x coordinate and y coordinate given, right? So what is constant for all these is x plus y is equal to whatever is the number of row. In this particular case, you can see 6. But what that value is not going to matter for you, because in your map you are going to have this value as a key. Hey, anything which has this value of x plus y, I don't know whether it is 6 or 4 or 5, like in this particular case, this value will be 2. But what your map will start to look like, okay, for 6 we have these many lamps. For 2 we have these many lamps. These are all my diagonals, by the way, diagonal map. But the important thing is whether this value is 6 or 10 or 15, that we don't have to determine, because I just say, okay, give me x and y coordinate, and whatever is the value for x plus y, I know all these points on that diagonal should fall into this diagonal.
Okay, that makes more sense.
Right. So same you can do for anti-diagonal also, like this. And then you will have a separate map for that, and whatever is the value, just keep adding. Like there was a value here, then there came another value here, for example. We will just say, hey, I have this value x minus y equal to some 5, for example. Here we already had a value. So there was one values, but now I got another one. So I will increase the count from 1 to 1 plus 1. So it will become 2, right? I will continue doing that. So yeah, that's it. And then I can quickly show the code, or we can move to the next one, or any other questions, feel free to ask now. Okay, no questions. So
could you also post the code on Slack?
yeah, there are many solutions better than me, but yes, why not?
Hey, Roger.
Yeah.
So you are saying you'll be creating a map where key would be the diagonal total of the diagonal.
X plus y or x minus y is my keys.
So is there any chances of that the total will be same in some of the diagonals?
Total will be same in the diagonal. What does that mean? So
Sorry,
can you give me an
example, if you see in the grid,
this
from
one?
this
So,
grid, like 1 to 1 is a diagonal, which
yes.
is showing, and similarly for the 3, like down as well, there can be chances of the same total.
Same total. So if you see x plus y was 2 there, right?
Yeah.
For that particular, do we do x plus y or do we do x minus y? You have to be very careful. I think we do x plus y, by the way. So for value 2, which other value you got? Only this point or this point, right?
Yeah. So this would be, for example, here also 1 1. This would be the 2. This would answer the 2. X plus y is 2. Correct?
Yeah. Yeah.
And for example, somewhere down as well, below the diagonal, there is also x plus y is equal to 2.
So x plus y is a straight line, right? Like
yeah,
mathematically.
Yeah.
So that's what we are trying to do. It's like a straight line, and anything on that straight line, we have a anything like any light on that line. I am counting how many light I have on that particular line.
So is this equation will be x minus y or something like that, and above will be x plus y, correct?
Yeah, one of this will have x plus y, one will have x minus y. Okay. For example, see, this 3 plus 3 is 6, right? So I know that this is x plus y.
Yeah.
This one will be x minus y.
Yeah.
So all these guys are x minus y.
Okay. And
Only value of x minus y is different.
okay.
Yeah, these are like plain equation of line. Like
Yes.
if you take a look at like math, simple math.
Yeah.
Okay, if you're looking at the diagonal, like the first top left, it is 0 0. So it's like 0. Okay,
Yeah.
the second one, if you take a look at the first row, 1. Okay, it should be 1 0, and the first row like first column, second one, it's also 1 0. So their constant is 1. Okay, that's how. Yeah, 2 and 3. Yeah, makes sense.
Yeah. Okay. Thank you.
Okay.
So maximum will be x plus y equal to 3, correct? In this
Sorry.
grade. So maximum could be x plus y can go to 3 in this grade, not 6.
No, it can go more, cause like there are not only 3 diagonals. Like in this case, there are 6, 7, 8.
No, the max x plus y can go to n minus 1.
Yep.
The maximum of x plus y can go to n minus 1. And then it could be n minus 2, n minus 3, n minus 4 until 0. Is it correct?
Sorry, your voice is breaking for me. So I can't hear much, unfortunately.
So I
No,
believe
my question is,
in this case it should be 2n minus 1.
the max,
So,
yeah,
okay, the question is how many diagonals could we have in a given grid?
Yep.
Okay. Yeah.
of n5.
Yeah, you can derive that. I mean, you can start with the diagonal and like main diagonal, and then you can see how many like you will have below and top of it. You will have equal number of those. So 1 plus 2 into n minus 1. So yeah,
2n minus 1.
yeah, something like that.
So there are 2n minus 1 diagonals and 2n minus 1 anti-diagonals.
Exactly, yeah, that's right. Okay, guys, so let's move to the last one. Or still, if you want to see code, we can quickly go through it. It's the exact same logic. I'm not even sure if anything interesting than this. We talked about all these maps. We have a map for row, column, diagonal, these two diagonals, like and anti-diagonal, these two. Then this is whether the lamp is turned on or off. Then in the beginning, as Gaurav was suggesting, that we'll go through each lamp, we'll update all rows, columns. Okay, let me do Control Z. Yeah, here. First you update row, then you update column, then you update your diagonal. Here you update anti-diagonal, and here you know, like, okay, what is this particular grid is. So that is one more trick which you should remember, like converting a two-dimensional array into a one-dimensional array kind of representation. So that is how we derived this one, that, okay, I know exactly where this cell belongs to, and this is a lamp, basically. So what is this chat? Use set for M5 instead of map. That is true. Yes. Yeah, we are not changing it. Or, yeah, yes, sure. So now let's go down. For each queries, this is very straightforward. We get the XY coordinate for each queries. And then we also find whether I found any turned on light there or not. So you can check all the maps. And if there was a, like, guy which was turned on, then you will say, okay, there was a light, then return 1. Otherwise we will return 0. And then we actually do the operation which we were supposed to do. that we will go in all these 9 directions in using this loop. We find our new coordinate, new x and new y, and then we check whether we have a lamp which is on or not. We just go ahead and then we update the count by 1, like we are reducing count by 1. So just we do this, and then finally we return this, and we continue doing this for all these queries. This is what we just talked about, right? So we can go to the last problem, which is medium today.
Yep, let's go. And also, like, one thing I want to say, thanks for sharing the logic, because once we understand the logic, it's like should be very easy to come up with the code.
Right.
So take the sessions to understand the logic,
Right.
okay, rather than the code, okay, and ask as many as questions if the logic is not clear.
True. Yep. And then today's last problem is minimum swaps to make sequences increasing. So you are giving 2 integer array. Like here, for example, A is 1354, B is 1237. And we have to make both A and B strictly increasing. Like they both should be increasing, not non-decreasing. And what you can do at every step is you can swap one index of A with another index of B, but index ID should be same. So you can swap, for example, A3 and B3, but not A3 and B2, something like that, to make both sequence strictly increasing. And the range is 1 to 1000 elements for A and B, and values are 0 to 2000. And then yeah, that's the question. So in this particular question, if you see, we had 1354 to begin with. Now of course A is not strictly increasing, but if we swap A3 and B3, so A3 was 5 and B3 was 3, then the sequence will become eventually 1357, and B will become 1234. So both will become strictly increasing in this particular case, and the number of swap was just one swap we did. Any ideas? Anybody did this problem? Okay, let me write some example to begin with. We'll change 1354. A was 1354 and B was 1234. 1, 2, 3, 4. After swapping these two, we have 1, 3. Actually, not, this will not work. 1237. Okay. 1237. 1354. 1237. So which one we swapped? I'm still looking at our example, by the way. 1354, 1237, swap A3 and B3. Okay, A3, it's like index is like this. So this means 1357, 0 base. So this is the guy which we are swapping. So this guy will become 1, 2, 3, 4. So both are sorted eventually. Yeah. So does anyone think that greedy will work? Looks like nobody has tried it. In fact, I have also not given enough time to this particular problem. That's why I kept it for the last one. So greedy may not work. I haven't, derived a use case, by the way, but the reason I believe it won't work, because swapping an element with another element can change my entire calculation further, because I don't know what I am changing something with. For example, if I'm changing something 4 with 5, that, or 4 with 99, that may mean totally different problem, because now my array will have something like this, 5, and then something after that, or something like this, 99, and something after that. So if some value is 99 and then we have to go right, I have to make sure that all other elements towards right has to be sorted. So that gives me the reason that it may not work. But unfortunately, I didn't get time to go through and greedy approach, find the counter case where it is not working. So I will leave that go and try to implement and find some use case. Or if you have already something, we can talk now. Otherwise, we will go with a DP approach. Okay, anyone? Should we go ahead with that then? Okay, so let's, I think yes, in that particular case, we are running out of time again. But what can we do? Because why DP works most of the time but not greedy is because the search space, you can say, or we are doing kind of exhaustive search in case of DP. We try to do all the possible combinations, like in all the dimensions, and then we can derive what result we are getting. So that's why, in a lot of problems, DP will always work. But if you find a greedy approach, and if it is working, then greedy will be it may have a better time complexity, because it made a decision and that decision was good for that particular problem. So you will get a faster runtime. That was a general thing. So what we can do for any swap, is, let me write here. Okay. Here and here, I have to finish the session, unfortunately, sooner. Let's look at it. When I'm at this particular ith index for both, there could be different things, I may either swap this with this, or I may not swap it. I can only take two decisions, right? So when I can take only two decisions, then we have a Boolean dimension here. So now you have two dimensions. One is your index is moving in this direction, and then you have, for each decision you are making, there are two more things which we can do. So you can think it like your DP array would look like something, call it DP some I and 2. This 2 will have two values. You can have true or false, or you can have 0 or 1, which will mean different thing. This may mean that, okay, I didn't swap anything in this particular choice I had. When I was making a choice at ith step, I didn't choose to do anything. One is saying, hey, I actually chose to make a swap there. So when one will happen, then we can say, since we chose to swap, our number of swaps should increase eventually, like however we are doing the calculation, we'll do it. So yes, we made one choice, one swap, and then we can move forward. So that's the structure so far we have derived, that hey, we have dpi2. And so what is the definition so far? We can understand about this part so far, why we will have two states. So significance of I is, when I am coming to I want to make sure that I keep count of all the possible, like, the minimum number of swap to make like everything from beginning till I minus 1 already in the increasing sequence. So this is what we are going to calculate. So that is what will mean, like dpi0 and dpi1, we have two states. So let's call it dpi0 is min swap to make a 0 to I increasing, when, this is important, now this will play a role, when we didn't swap at ith position, like current choice. Same is dpi1, exactly same, but only thing is, in that particular case, we are swapping. Exact same, but we chose to swap. Okay. So there will be some transition functions which we will derive later with examples. There are a lot of cases, unfortunately. At least there are 3 cases. But what is the, like, base case? So base case is, okay, what if there is only one element? So dp00, when there is only one element and I didn't choose to swap it, then I can say, okay, 0 was my answer because there was one element and no swap, so 0 is fine. There was 0 element, or let's say this is called one element, because 0th index is first, and we choose to swap. So it doesn't make sense. Why would we do that? But we are evaluating all the possibilities. So if you remember, we are saying that we chose to swap it. So we are adding one cost already here. So this could be your first state. And your example could have been maybe say like 2, 3. These two arrays, A equal to 2 and B equal to 3, they are already sorted. So even though there was no need, but we choose to swap. So what we did, we made A equal to 3 and B equal to 2. So if we spend that cost, so we are putting, like, one cost here. That's the reason. So that was our base case. Now what should be the final return? Like suppose magically everything is working, then your result should be the last guy. Like when you finally reach this place with all these two states, like, dp, let's call dp n minus 1 0 and dp n minus 1 1. That was your final case. Using these two approaches, you reached there. So your answer is, okay, whatever gives me minimum, that is my minimum cost. So that is the definition here. Here is your base case. Then here is the final return. And then the core logic is transition function, which we have to derive, which is the core, logic. So we'll work on that now. I will erase this. Is that okay? We'll put some example and then we will derive that soon. So let's take some example, like, case one. Suppose you had everything on top is A and bottom is for B, 2, 4. This is the case when A is increasing, B is also increasing, right? This is increasing, this is increasing. And when we are swapping anything, like for any ij, like if you think like there was a swap here, you have I minus 1, you have I, same here, I minus 1 and I. So this guy will go to here and this guy will come here after the swap, right? So what is important for us also to know the relation between this guy and this guy, because something came from bottom diagonal, let's say, to top, which became adjacent to this guy. So he will be interested to know whether he is going to be increasing or not. Then things may change. Similar for this guy too. Similar for this guy actually too. Like anything coming from top to bottom, and if it is not directly increasing, then maybe that's like a different kind of decision. But in this particular case, I know whether 5 will come down, 2 will be okay with it. If 4 will go up, 3 will be okay with that. So this is the case where everything is fine. Like, that doesn't matter what you do. Like, both are increasing, plus let's call it something like cross, maybe cross increasing. So for this particular case, doesn't matter what we do. So what will be the transition function? Transition function is when you derive something, like in this particular case from maybe previous state. So dpi 0 will become what? Like doesn't matter what I do, as long as, so okay, also one more thing. Again, I will try to clarify. dpi 0 means that, hey, in this particular case, I am not going to do swap. So no swapping in this particular state. So what can happen? It will say, okay, if I'm not swapping and if it is a good state, then what we will have, whatever we had from the previous state, I minus 1, 0. Using whether you did swap or not, I don't care. Just give me that, whatever was the minimum. Sorry. And that should be it. For this particular case, you do swap, doesn't mean anything whether you swap or not. You can just have this thing. But what if I say, okay, dpi1, in this particular case, we are saying, okay, we have to do swap. So as soon as I say I am doing swap, I should first make sure I am adding 1, because I made that decision. Now, what about the previous state? What was happening at I minus 1? Does that matter how I came here? That doesn't matter for this particular case, because everything was increasing. So whatever was the minimum, again, I will take that and I will move forward. So same state, just only thing is that this time we paid 1 extra cost. So that was case 1. Now, case 2 is when cross is not increasing. So I can have another example where like Suppose you have 3 and 5 here and 6 and 7 here. So A is increasing, B is increasing. This is A, this is B. But look at the cross. If 7 gets swapped with 5, then 3 will be okay. But 6 will not be okay here because 5 will be less than this. So in this particular case, we have a different case. What can we do? So this is case 2. So in this particular case, let's look at what we have, DPI0. So a decision is made that, okay, we will not swap. So if we are not going to swap in this current instant, then what we did in the previous step was, I will come to this, DPI minus 10. So this is that case when this guy is increasing so far, like everything is increasing. So can I come from I can come from DPI minus 10 because we didn't swap last time and we are increasing, and so we don't swap this time. But I cannot come from a state where we had swapped previously, because if you would have swapped 6 with 3, then you cannot make, like, first of all, it was not a valid state also, but you cannot use DPI minus 1 for anything here. So you have to use only this particular case. Then when you didn't swap previously, then you can still continue to choose not to swap again. If it is like not very clear, then I would suggest, like, watch later and then again watch this. That's why I decided to do it late, because it was actually more complex than the hard problem, at least for me. And I haven't spent too much time, but still I felt that way. So this transition, we are going to choose one here. What does that mean? That, okay, you have to spend one extra cost, because we are saying, hey, I am going to swap this time. So if I'm going to swap this time, what can we do here? Can I swap when I didn't swap last time? So what we are saying now, if I am swapping, like, so 7 will come here, 5 will come here, and 3 and 6, right? I cannot swap unless I swap these guys also last time. Had I swapped these guys, then I would have 6 here and 3 here. Then everything would have been okay. 6, 7, 3, 5, all fine. But if I haven't swapped previously, then this won't work. So my state is now, I cannot use not swapping last time. So I can only do this if I swapped previously also. So for this particular case, my transition function will be like this. DPI0 can come only from DPI minus 10, and DPI1 can only come from DPI minus 1. So yeah, that's second case, and then we will go to the last step, and then we will just finish it. I'm going to clear my drawing because I don't have enough space here. So case 3 is when case 3. So you can have things like this: 3, 2, 1, 7. Here, diagonally, it is actually good. If you swap, things will be okay. But these guys are not in increasing order. It's the other, like, case. In first case, we have both happy. In second case, first one was happy. In this particular case, it's the second one is happy. So diagonal is fine, but it is not increasing. So we will have to derive something, how the transition will happen. So let's look at dpi0. If we are saying that, okay, we are not going to do any swap. If I am saying that, okay, we will not do swap, then how it can work? Means if we are saying, I will keep 2 here, I will keep 7 here, then do you think 1 and 3 should have swapped already? Because if they do not, then it's not good, because your increasing sequence will not be maintained. So in this particular case, in previous step, a swapping must have happened. So you can come here only if you swap previously, like this. And here dpi1. So 1 for sure, because we just said that, hey, I am swapping no matter what. So, okay, in this particular case, we had 3, 2, 1, 7, and we chose that, okay, we are going to swap. So 7 came here and 2 came here. So now it is fine. It is fine as long as these guys didn't decide to do any swapping among themselves. Because if they decided to swap, then it will become bad, because this guy will become 1 and this will become 3. Then 3, 2 is not good. So what we are forcing that don't swap here, then only I can do this swapping. So that way, this will become dp I minus 1, 0. And that's it. Like you will have these 3 cases, these, like, transition functions for all these 3 cases. And then finally, we already know what we are going to return. So let me show you the code pretty fast, and then look into this after you, like, spend a little bit time. Then it will hopefully will make more sense. And we are also running out of time, so let's do it quickly. It's exactly same story which we talked about. So this is what we were talking about. What is DP doing? We calculated whether both are self-increasing or cross-increasing. And we can determine that just by looking at their neighbors. And then we have these 3 cases which we just discussed. This is first case when both are increasing. And we just derived the equation in front of you. It's the same example I took. Else if second case, else if third case. And as we talked about in the beginning, that what we will return finally. So this is what it is. So in this any DP problem, once you are able to figure the transition functions and base cases, then it's basically mathematically, like, easy to write. But yeah, I would suggest go spend some time. Is there any questions?
No.
No questions. Okay. So I will stop the recording and we'll talk later.